Have a good day. Okay, so this is a recorded topic for the divergence theorem. So this topic is actually the continuous topic after the Stokes theorem. Okay, so I'm going to open Paul Dawkins' ebook. Okay, so this is the divergence theorem. So the previous theorem that you have learned during previous class is the Stokes theorem. Okay, now we will see the divergence theorem. So in this theorem, it uses the dot product for the vector, and this theorem applying or transforming the double integral to the triple integral. Okay, so I'm going to read the theorem. Let E be a simple solid region and S is the boundary surface of the solid with positive orientation. Then the vector F is the vector field whose components have continuous first order partial derivative. Then we have the double integral for the surface. That is the dot product of the vector and the surface that is equal to the triple integral for the boundary surface of E, divergence of the vector F, and we have a dv for the three-axis. Okay, so the meaning here when it's stated components have continuous first order partial derivative. Okay, continuous first order partial derivative means that we have the vector f that can be evaluated their first order partial derivative. Okay, then if the vector f is the vector that we can find the partial derivative, therefore we call it as a continuous first order partial derivative. Okay, so we'll see example 1 regarding the divergence theorem. The question is to use divergence theorem to evaluate the integral, and the vector field f is given here, and we have the surface S consists of the surface between z equal to 4 minus 3x squared minus 3y squared. Then we have a z between 1 to 4 on the top, and we have the surface between x and y axis. Okay, so this is actually the circle, and we have the limit for z between 0 to 1 on the side and z equal to 0 on the bottom. Okay, so we represent all the conditions here. Okay, so number 1, number 2, number 3, okay, number 4, and number 5 here on the graph. Then we have this kind of situation. Okay, so for this one, we can let when x 0, when y 0, so z is 4. Okay, and we have this kind of a solid. It is close to a cylindrical or spherical. Okay, but the closest one, it is similar to the cylinder. Okay. Okay, so we have the limits. So the circle is the area between x and y plane. Okay, so in this case, when we refer to the divergence theorem, okay, we have to convert the double integral to the triple integral. And we see that this vector field f is a function or the vector field that we can find their divergence. Okay, what is the meaning of divergence for the vector f? So remember in the previous class, this is a vector f, so we can differentiate this part with respect to x, differentiate here with respect to y, differentiate here with respect to z. So this vector f is a continuous first order partial derivative. It means that we can find the partial derivative for this vector f. Okay, so if we cannot find the partial derivative, then it is not a continuous first order partial derivative. Okay, so in this divergence theorem, when we want to express the triple integral, we have to decide that dv, whether we are going to use the Cartesian in 3D, okay, for example, dx, dy, dz, or other 3D coordinate system. Okay, so other 3D coordinate system will be based on the cylindrical or spherical coordinate. Okay. Okay, so uh, it is will be a complicated if you want to use spherical, but because of the solid that we have figured out here, it looks or close to the cylinder. So we are going to apply the cylindrical coordinate system in this triple integral. Okay. Okay, so the coordinate system, if we want to use this cylindrical coordinate system, will be based here. Okay, x, y, z. So this row refer to our radius. Okay, r cos theta, r sin theta, and so on. Okay, when we refer back, we have to find out what is the limit for x, y, z axis in the cylindrical. Okay. According to the limit here, this is in terms of Cartesian. So if we want to decide that we are going to work in cylindrical, therefore this x should be converted to the one related to the r. Okay, so our equation of a circle is x squared plus y squared equal to r squared. Okay, so we can factorize this x squared and separate them with 3. Okay, in other words, we factorize 3. Okay, so the one in the bracket we have here, x squared plus y squared. Okay, then we have this equation z in terms of r will be 4 minus 3 r squared. Okay, and then this is the radius value for the xy plane, because the figure, this is a standardized equation for the circle. So z will be the limit between 0 to 4 minus 3 r squared. Okay, so this 4 minus 3 r squared comes from this limit. Okay, so this is the one in the Cartesian, convert to the cylindrical will be here. Then we have radius value with, between 0 to 1 that comes from our equation of a circle. Okay, so we have radius of 1. Okay, theta is the rotation between xy plane. Okay, so we have from 0 to 2 pi. Okay, so we have to decide whether dv will be dz dr d theta, or d theta dr dz, or dr dz d theta, and so on. Okay, how to decide? Okay, depending on the limit. Okay, so the one that does not contain the fixed limit, okay, like this limit for z should be the one at the inner part of the triple integral. Okay, not at the outer part. So r theta is the contain fixed limit. So we can have, for example, dz dr d theta, or we can have dz d theta dr. Okay, so there's no problem with either one. Only that we cannot have the dz as the outer part. Okay. So we have decided that in the divergence theorem, the dv that we are going to use in the cylindrical will be either dz dr d theta or dz d theta dr. And then we are supposed to evaluate the divergence for the vector field F. Okay, so divergence refer to the partial derivative for this vector F. Okay, that means, okay, so we have this vector field F. So divergence of F means, okay, so we have to differentiate, evaluate the partial derivative, okay, for xy with respect to x. Okay, and then plus the partial derivative of dy for this negative half y squared, and the partial derivative for z for here for z. Okay, so when we continue here, we have differentiate this with respect to x, then we have y. Differentiate this with respect to y, okay, then we have actually negative half times 2, that is equal to negative 1. So we have minus 1y. Differentiate this with respect to z, then we have plus 1. Then we simplify, okay, so we got 1 here. Okay, so this means that we have this divergent f that is equal to 1. Okay, so we identified already that the divergent f is equal to 1, and we have identified that we are going to use dv as either dz dr d theta or dz d theta dr. So you can choose either one. So if we choose, for example, dz dr theta for the dv, okay, then we have this condition. So this will be the limit for z. Okay, then we have this one, the limit for radius. This is the limit for the theta. Okay, so the dv in the cylindrical, okay, the dv in the cylindrical is equivalent to r dz dr d theta. Okay, so first we are going to integrate with respect to z. Okay, for example, okay, so integrate here, so we have zr. R is outside, so we are going to substitute when z is 0 and 4 minus 3r squared. Okay, so this will be the limit for r, then this is limit for theta. So here we have the r d theta. Okay, so we substitute here for z. Then we have 4 minus 3r squared, but there is another r. So we just times up as 4r minus 3r cubed. Okay, then we have the r d theta. So here is the limit for radius and the limit for theta. Okay, so we get at this stage. Okay, so to proceed here, another direct integration. Okay, so here will be 4r squared over 2. So simplify with 4, then we have 2r squared. So this comes here. So this will be 3r power 4 over 4. So it comes here. And then substitute the r when it is 1 and then 0. So we just need to substitute when r is 1. Okay, there's no use here for 0. So we have 2 minus 3 over 4. Then we have this constant 5 over 4. And then we proceed at this stage. Integrate this with respect to theta. Then we have 5 over 4 theta. Okay, for 5 over 4 theta. And then we are supposed to substitute when theta is 2 pi and 0. Finally, we have this one. Okay, so this is an example for the divergence theorem. Okay, so if there's any part that you don't understand, please ask me, okay?